You've been solving equations for a long time. And pretty much most of the equations you solve, they have solutions that are numbers. They might be real numbers, they might be complex numbers, there might be more than one solution, but you've been solving equations and finding solutions that are numbers. For the first time, we're going to solve equations for which the solution is a function. And what's going on here? Well, we've learned this year about two new operations who take functions as inputs and give functions as an output. So think of the derivative. I can take the derivative of a function, and the result is another function. Whereas every other operation I've learned about before calculus, I could take the cosine of a number, and I get a number out. Or I could square a number, and I get a number out. So differentiation and integration, they are two new kinds of functions that take functions as inputs and give functions as outputs. So we will be solving equations that contain derivatives. So I ask you, how do you think we're going to do that? Write your guess. There's a little line for you to write your guess. So here's the definition. A differential equation is an equation that contains a derivative. This word order, that doesn't necessarily need to be a capital O. The order of a differential equation, look what I typed there. I typed diff EQ. Really, it should be differential equation, but if you want to sound cool when you talk about differential equations, you call them diff EQs. You'll probably take a class in college called differential equations, and you'll talk about your diff EQs class. So the order of a differential equation is the same as the degree of the derivative. So an equation that contains a first derivative is a first order differential equation. An equation that contains a second derivative is a second degree equation. Second degree differential equation. Second order differential equation. So sometimes we can solve a differential equation by just thinking of the right antiderivative, the function that has the correct derivative. So this is from your textbook. Find all the functions that satisfy this differential equation. The derivative of y is secant squared of x plus 2x plus 5. So these little pieces, the secant squared, the 2x, and the 5, they're all functions for which I can think of an antiderivative. And I know that the antiderivative of a sum is the same as the sum of the antiderivatives. So I will answer this one by saying y must be, what's the antiderivative of secant squared? It's tangent x. The antiderivative of 2x, I could come up here, that's 2 times x. I'm going to increase the exponent by 1. So that was x to the first, now it's x to the second. I'm going to divide by the new exponent, so 2x squared over 2 is x squared. You have no obligation to show that step if you can do that part in your head. The antiderivative of 5 is 5x. And I have to remember that there are infinitely many functions that have the derivative that was given, because there could be some constant, that's a plus sign, added on the end. And when I took the derivative, it wouldn't have mattered. I would get the same dy dx value. So this is tangent x plus x squared plus 5x plus c. If you forget the plus c, you will lose points. So that answer that we had that had a plus c on the end is called the general solution to a differential equation. If I had been given some ordered pair, some point on the y function, then I would be able to figure out the value of c. I wouldn't have any variable like a c, like a plus c left in my answer. That problem, which is a differential equation combined with one ordered pair from the function you're trying to find, is called an initial value problem. And the solution to an initial value problem is called the particular solution to the differential equation. If it has a plus c, it's a general solution. If you can figure out what c is because you have more information, then the function you're giving as your answer is the particular solution. So this next example, again from your textbook, says find the particular solution to this equation. Dy dx is e to the x minus 6x squared. And I've been given this one ordered pair. So 1 is the x and 0 is the y. So we start by finding the general solution. So thinking of an antiderivative for this derivative. So y is going to equal the antiderivative of e to the x. That's the easy one. That's e to the x. minus, so this would be, I'll write it down here, 6x to the, increase the exponent by 1, and divide by the new exponent. So 6x cubed over 3 makes 2x cubed, minus 2x cubed, plus a constant. Now we're going to stop and we're going to figure out what c is because we have enough information to do that. So I'm just going to leave the board as it is and sort of squeeze my work in between here. So I'm trying to figure out what c is, and I have this ordered pair. I know that when x is 1, y is supposed to be 0. So I'm going to plug in 0 for y. E to the 1 minus 2 times, I'm plugging in 1 for x. So that tells me that 0 is equal to e minus 2 plus c. I want to figure out what c is, so I'm going to isolate c. I do that by subtracting e and adding 2. So subtracting e and adding 2. And I find that negative e plus 2 is c. So this that I started with is called the general solution. Since I've been given an ordered pair with my differential equation, this is an initial value problem, and I'm going to take one last step, which is to write my final answer. Give me 1 second. The final answer is that general solution, but with the correct c plugged in. So y equals e to the x minus 2x cubed plus, what's c? It's negative e plus 2. Final answer.